topic will be inverse magnetization problem in polymagnetic context, as it's the primary direction now in the FACTAS team. And in particular, I will focus on the aspect of the field extrapolation, model-based field extrapolation. So this is something I'm particularly interested in, because this is a problem that is pertinent to this context, to the context of the polymagnetism and particular experimental setup. But the problem is, of course, more general than that, and I think it is quite understudied and generally overlooked. So, and also it fits very well into the type of problems, perimeter of problems that FACTAS team is working on. So, okay, let's start with the context of the polymagnetism. So, polymagnetism is essentially the study of the history of the magnetic field on Earth, or potentially also other planets, and this is done by analyzing rocks which contain some remnant magnetization. Well, that's one way of doing it. And so the way it works is that the geophysicists pick up those rocks on which they have some information, and those are the specific rocks which are igneous rocks. So they are rocks which were which come from, for example, lava, and as they were in the high temperature, so ferromagnetic particles in those rocks were aligning along the exterior magnetic field, and as they were cooling down, this orientation stayed frozen there. So now they still they act as a magnet, which have a specific polarity, and analyzing this magnetization gives a window into the past behavior of the exterior field on Earth or other planets. And so for geophysicists, that opens a lot of horizons. So this is a rather important problem, and the issue is that the magnetization cannot be measured directly itself. So it can be measured through the field that it produces. So here we can see the setup, particular experimental setup of colleagues in US. So they use squid magnetometer to measure the magnetic field produced by a sliced rock. So here we can see the slice of a rock, and it's glued on the support under this huge machine, which is actually embeds magnetometer, but mainly the cooling device. And the magnetometer sees the sample through this sapphire window, which is inverted here upside down. And as a sample moves, so the support under moves horizontally, the measurements are collected point by point in the direct vicinity of a sample, but above it. So schematically speaking, we have the magnetization vector, which models the sample, and it is we can assume for simplicity here that it's planar, because as I showed you in the previous picture, it is a thin slab. And so it's the vector of three components, and it's the magnitude and the direction can change in the sample from one point to another. And at some lift of h, so at some distance h, the magnetic field is measured, and the particularity of the setup that only one component of the magnetic field can be measured. So it's only the vertical component of the field is measured in this horizontal plane. And now, given the values of the measurement of this magnetic field, the goal is to learn something about magnetization that produced it. So to which extent it can be recovered and how can it be recovered. So in other words, for example, we have this magnetization vector in the region S, which, for example, is given by this three functions, and it produces the field B3 at distance h from it. And the inverse problem is, given this field, to reconstruct them, these three functions. So we want to reconstruct three functions from knowledge of the one. And here it's this equation is included for only reason that just to show you that there is a mathematical model. We're doing the reconstruction we're talking about is there is underlying mathematical, physical model that relates magnetization to the field, and I promise that's the only equation I show. So we just this is just to say that it's that there is a strict relation between the quantities that between what is measured and what we want to reconstruct. So the reconstruction of the magnetization from the field is a severely ill-posed problem. So there is the solution may not exist, but what is even more crucial that is non-uniqueness of the solution, and it's the solution is lacks stability. So let's start with the lack of uniqueness. So just to illustrate what I mean by this, so suppose we have a magnetization vector on the left here, and it produces the field at distance h like this. So but then we can also find another magnetization here on the right, and this magnetization vector produces exactly the same field. So from knowledge of the field alone, we cannot reconstruct uniquely the magnetization distribution. And this non-uniqueness is inherent to the general continuous model. So this is something that cannot be improved by improving the methods. So here we should just, the only way to deal with it is to understand what representative in the equivalence class, in the class of equivalent magnetization, we are reconstructing. So, for example, we can say, okay, let's search for the solution, the reconstruction, let's search the solution which has the minimum L2 norm, for example, or we can choose some other criteria. So, but non-uniqueness in general is not necessarily a big issue, because in practice, physicists are interested not so much in the particular distribution of the magnetization point by point, but on the general, its general characteristics. For example, they want to know what is the overall magnetization of a sample. So is a sample how strongly it is magnetized, and in which direction. And these properties of the magnetization, they are unique over the equivalence class. So, and the second issue is instability, and this is something more nasty. So to illustrate this, again, I show the picture. So suppose on the left we have the magnetization like this, which is, by the way, generates exactly the same field as I showed you before. So that's equivalent magnetization to another magnetization that I showed you before. The field is the same. So, and now on the right we have magnetization which is not equivalent to the magnetization on the left, but produces the field which is extremely close to the one produced by the first one. But yet magnetization is not that close. For example, if we look at compare this last component of the magnetization, they look quite different, and yet the difference in the produced field is of order like 10⁻⁸. So the reconstruction issue is very unstable. And by the way, here M2, so this magnetization on the right is actually a reconstruction, is an attempt to reconstruct magnetization M1 from the field that it produced from B3. So since smoothly passed to the reconstruction or the inversion of the field. So I'm showing you exactly the same picture, but now I'm renaming M1 into original magnetization, and its reconstructed values I called M_inf. So that this is what we reconstruct, and now we ask ourselves, well, how can we improve that? So note that here we have measurements of the field over the square, which is the size the square, which is minus 1 1 minus 1 1. So it's fairly small square. But suppose we have larger regions. So suppose we have measurements over the larger region, minus 2 2 square. Then the magnetization reconstruction improves a lot. So I'm just go back and forth between these slides, and you see that the reconstructed magnetization got much closer to the original one with a larger region. And of course, this is obvious that the more data you have, the better result you expect to obtain. Yes, but what if you have more data, like more dense measurements, but still over the small region? So the issue in experimental issue is that you cannot measure too far, because then since the fields are so in polymagnetism, the fields are so weak that if you go further from the sample, you will be measuring essentially noise. So you cannot afford measuring over a large region. But this is what you need for the methods to work the best. So now the question is, can we start with the original measurements and with the dense measurements on the small set and somehow unpack them into the larger set? So this is the issue of the extrapolation of the measurements. So I promised you that I showed you only one equation in this presentation, and I didn't lie, because it's exactly the same equation. So, but here it's just to stress that we by extrapolation we mean that mapping the measurements on one small area into measurements on a larger area, but respecting the structure of the problem. And the structure of the problem is the structure of the underlying integral operators, which are related to this integral equation below. So we want to start from the field on the blue square and obtain it on a much larger square, but potentially even on the entire plane, this green region. And is it a fantasy? Is there a possibility for this at all? Or actually we can do it. So suppose that again we have the same field, and now we want to we can extrapolate it not just to the 4 times larger rectangle, but we can even extrapolate it to 100 times larger area. So it means we took the one source and we kind of isolated it from everything and obtained the field that it produces alone without any contamination. So here the extrapolated field is on the rectangle minus 10 10, which is 100 times larger. And this is the original field, which was produced by the same synthetic magnetization. So the difference is extremely small. So this is like a couple of % difference, error localized in some small areas. So this is quite surprising extrapolation result that it's possible to achieve. And of course, the situation gets much worse if we put ourselves in a realistic setting when we have non-exact data. So here everything was synthetic, but in reality we have noise, and then the results are not as impressive, but still fairly good. And this is just one of the extrapolation method, for example, that I showed you the results of. But there are others that can allow to treating the volumetric samples. And now, so we were dealing with the extrapolation from small square into the large square or the entire plane of the one component of the field. But once we know the component of the field on the entire plane, we can actually again use mathematical structure of the that the field obeys, so the harmonicity of the field in particular, and we can generate two other components. So we from altogether from knowledge of one component of the field on a portion of the plane, we can obtain all three components everywhere actually. So in idealistic setting. So of course we can play this game, and but when we have noise, there is some limit to this, right? So we cannot start with something that is contaminated by noise 50% and obtain everything clean and nice. So there's a call for to investigate what is theoretically possible with this. And of course, we could also extend this results to other problems in the magnetism and beyond, because the extrapolation problem overall is a general. So here we want to extrapolate the measured data into the area where we cannot, which are not accessible to measurements, but yet respecting the structure of yet respecting the underlying equations of the model. So I'm a bit out of time. I'm sorry, and thank you for your attention.
Thank you.